So other identities, kind of a bland name for a section, right? Other identities. But these are the last of the identities that we're going to memorize. So the first new set of identities we call the double angle identities. And the double angle identities, you've kind of already seen in the last proof in the previous set of notes. We actually kind of derived the double angle identities. These show up quite a bit, and these are very, very important if you go on to take calculus. So here's what the double angle identity does. It takes sine of twice an angle x. That's how it gets the name, the double angle twice x. And it expresses it in terms of the single angle x. So sine of 2 times x is the same as 2 times sine of 1x cosine of 1x. Okay? Very nice. Expresses a double angle in terms of single angles. So in calculus, typically what we do is we go in reverse. We'll have an expression like that that's hard to deal with in terms of calculus. And if we can condense it and write it like the single trig function, it's much easier to work with. Okay, so these are an identity. They're true for all values of x in the domain. The other identity is cosine of 2x, and it's also very, very popular and very, very important. It's equal to 3 different things, though. But the main one, if you're just going to memorize one, it's the top one there. And that sure looks a whole heck of a lot like what? It looks a lot like Papa Pid. What's the only difference? The difference, right, minus. The difference is the difference. Papa Pid is cosine squared plus sine squared, and cosine of 2x is cosine squared minus sine squared. The other two are just different versions of it, and you can easily obtain those from the first one simply by using a Pythagorean substitution. So it might be when you're doing a proof or something, you want to write it exclusively in terms of cosine or exclusively in terms of sine. So if you memorize this one here, you can easily do a substitution on either one of those with a PID and get the other two. So it's not necessarily that you memorize them, but having them memorized could save a little bit of time. Okay, so let's go ahead and prove this identity right here. Bless you. How are we going to prove it? Right, we don't, here's the thing, you don't want to use cosine squared minus sine squared to prove this because it's part of the same identity. So you don't use a word to define the word, right? So what we'll do is we'll use the composite identity, and this is what we did on the last example in the previous section. We'll call 2x, not 100x minus 98x, but x plus x, yeah, because we're trying to introduce single x's. So cosine of x plus x. And now we can use a previous identity, the composite identity, selfish cosine, right? So it's cosine of the first, cosine of the second. And what happens with the sign? Changes, and if it was plus, now it's minus, and then it's sine of the first, sine of the second. And now if you combine like factors, you get cosine squared of x minus sine squared of x. And that is essentially the proof of the main version of this identity, cosine squared minus sine squared, which looks a lot like Papa Pid. And so then how are we going to get the other version of it? Well, let's see. I want it to be exclusively in terms of cosine. So here's where we will maybe put parentheses around that one. And then I can do a substitution with sine squared in terms of cosine squared. Do we know what that is? What is it, William? What is sine squared in terms of cosine squared? Marshall. If you don't have your identities memorized, it's almost not even worth showing up for class because we need them to move forward. What's that? No. Anyone? Yes, save us, Joey. 1 minus cosine squared of x. Thank you. Sometimes there are just not enough front row seats on the 50-yard line. Okay, great. Sine squared of x is 1 minus cosine squared of x. That's Papa Pid. And now if you distribute the negative, you get cosine squared of x minus 1 plus cosine squared of x. Carefully distributing. And then you can combine your two cosine squareds. They're like terms. One of them over there plus one over there makes 2 of them. 1 for you and 1 for your friend. Sharing is caring. And now that looks like the right side, so we are done. Like Charlie done, the bootmaker. So there's kind of two proofs in one right there. You can kind of see the proof on the third line for the general identity. And then if you need to get to, in terms of cosine squared or sine squared, you would do the Pythagorean substitution. And the other one would be just as easy, almost easier, replacing cosine squared with 1 minus sine squared. Okay, so the proof of this one, guess how you're going to prove this one? If you had to, like on an exercise or in the worksheet or something. You would have to use the composite identity. And when you expand it out, you'll see that you get 2 sine x cosine x. But they show up so often, you want to memorize these. All right, so what is 2 sine x cosine x equal to? Sine of 2x, right. 2 sine of 1x cosine 1x is equal to sine of twice x. And, of course, what is cosine of 2x equal to? Minus sine squared. Cosine squared minus sine squared. So notice the cosine one is 2 terms, and the sine one is 1 term. Yeah? No. But you should be able to get the other 2, if need be, by doing the Pythagorean substitution like we did right here. Okay, let's look at example 2 then. Cosine of x is negative 2/3, and sine of x is positive. So this is kind of like a modified 2's clues problem. We want to find cosine of 2x, sine of 2x, and tangent of 2x. Well, in the past, I might have just asked you for sine of 1x, tangent of 1x. So the first thing we need to do is, like we would normally do, we need to figure out where x lives based upon the 2 clues. So let's go ahead and draw a little picture. The ratio that gives us is negative 2/3, and it's a cosine ratio. So where is cosine negative? Yeah. 3 I like. 2 and 3. Yeah, 2 and 3. X is negative, and cosine is negative, and vice versa. And then sine is greater than 0 in which 2 quadrants? 1 and 2. So the overlapping quadrant is quadrant 2. So we're in quadrant 2. So there's our angle theta. Drop the perp, and now you can label your reference triangle. Cosine is x over r. So it's going to be a 2 and a 3, and which one has to be negative in this case? The 2, right. 3 is always positive, so 2 is negative. And now by the Pythagorean theorem, the y value is positive. Square root of, or 3 squared is 9, minus square root of 2, or negative 2 squared is 4. So it becomes the square root of 5. And it's positive because we are up. If we happen to be in quadrant 3, it would have been negative square root of 5. So, of course, now that we know all 3 sides, we know all 6 trig ratios for the angle theta. How am I then going to find, or I guess we call it x. We can call it x here instead of theta. Kind of the same thing. In this context, x is the angle. So how are we going to find cosine of 2x or 2 theta if I only know information about 1 theta? Well, is there a way to express 2x in terms of 1x? I think so. I think it's called the double angle identity. So let's go for it. Cosine of 2x is equal to what? Good. Cosine squared x minus sine squared x. And now, because I was able to express it in terms of single x's, now I can use the information from my little diagram here. So as I work down, cosine squared minus sine squared. That's what you want to do. Take it out of the condensed notation, and you're actually squaring the ratio. So now we'll go get the cosine ratio. Well, that was given. The cosine ratio is negative 2/3. And the sine ratio is what? Square root of 5 over, it's y over r, yeah, over 3. And now it's just a matter of evaluating. So a negative number squared, you get 4/9, becomes minus 5/9, and you end up with negative 1/9. So kind of neat. We don't really know much about angle x, but we're still able to find the trig ratios for it because we can express it in terms of single x. Similarly with sine of 2x, Sine of 2x, if I could express it in terms of single x's, that'd be fantastic. What is it equal to? 2 sine x cosine x. So again, before you start doing any worksheet problems, whether it's tonight or the morning before it's due, you want to memorize the identities first, okay, so that you don't have to look them up every time. Now I can just plug in here, sine of x, cosine of x. And it should be the same ratio as we had over here. Sine of x is square root of 5/3. Cosine of x was given. It's still negative 2/3. So now when you multiply straight across, you're going to get negative 4 square root of 5 over 9. And there's the simplified exact value. Now tangent of 2x. Did we learn double angle identity for tangent of 2x? No, but we know how to get it from the sine and cosine, right? Because tangent of 2x should be equal to what in terms of sine and cosine? Yeah, sine of 2x over cosine of 2x. That's an old identity, right? That's the ratio identity. As long as the angles are the same, it works. Well, I already found sine of 2x and I already found cosine of 2x. So this one's kind of nice. I'll just take the ratio of the two. So it's negative 4 square root of 5/9 divided by negative 1/9. And now you can stay, change, flip, and you end up with what? Bless you. Positive 4 square root of 5. And there's the simplified exact answer for tangent of twice the angle whose cosine is negative 2/3 in quadrant 2. Fun, 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 fun. Go Gadget Identities. Did you ever watch Inspector Gadget? The cartoon, not the movie with Matthew Broderick? Both of them. Yeah, it was good. Go Gadget. You could call your own identities out. They don't have to come out of your trench coat or hat. They come out of your head. Why was that minus up there? Is that what you're asking? Why is it minus? Yeah. Okay. X squared plus y squared equals r squared. So negative 2 squared plus y squared equals 3 squared. Negative 2 squared is positive. It is positive. So you get positive 4 plus y squared equals 9. But you have to solve for y squared. Yeah. So when you bring it across, it does become minus again. So yeah, take more steps if you need to, because you don't want little careless mistakes to derail you. And now all it takes is one little negative right there. Okay, cool. Any questions on example 2? Any more questions on example 2? Must be a big submarine. Yes. Yeah. I'm not going to give you the double angle identity for tangent. You could derive one easily by using the composite identity. If you want to use it, that's fine. You can derive one, but I'm not going to make you memorize it. So you could just do it like sine of 2x over cosine of 2x and use those separate identities. It doesn't show up nearly as often. But the sine and cosine, very important. All right, let's look at example 3. We want to write cosine of 3 times x in terms of cosine of 1x. What do you mean pull a 2 cosine out? The angles? No, the angles are kind of sacred. You can't factor angles out. All you can do is use identities to substitute them in. So if I'm trying to write everything in terms of 1x, again, I do have to start with, there's not a triple angle identity that we memorized. So we can start with the composite identity. And we can write 3x as what? 2x plus 1x. Or x plus 2x. It doesn't matter. Now I can use the expansion of the composite identity, cosine of the first, cosine of the second, change the sign, sine of the first, sine of the second. And this is similar to the last problem we did in the previous notes. At that point, we had to use the composite identity again to write 2x as x plus x. But now we don't need to do that, do we? Now we can go straight to our memorized double angle identities. cosine of 2x is equal to what? Cosine squared minus sine squared. Are parentheses important here? Very. Yeah, because we're going to have to then distribute the cosine. And then sine of 2x, parentheses are okay, but they're not as critical here because remember, sine of 2x is just a single term. So 2 sine of 1x cosine of 1x times sine of x. So at least now at this point, all of our angles are what? Same x. That's good. But now my task is to get rid of anything that is not a cosine. Namely, get rid of any sines that we have left. Okay, so let's go ahead and do that. This is where knowing the other two identities for cosine of 2x could save you a line or two, because there is a version of cosine of 2x that's already in terms of cosine. But if not, let's go ahead and change it right here in the problem. Minus parentheses times cosine of x. So all I'm doing is I'm inside there putting parentheses because I'm about to replace sine squared with what? 1 minus cosine squared. And again, that's a two-term substitution. So anytime you're replacing a one term with a two-term, you got to be careful, especially if there's a negative out front. And then over here, since it's just something times something, there's nothing to distribute. We'll just combine like factors. I get 2 sine of x times sine of x, which is sine squared, times cosine. And again, pay attention where the squared goes. All right, then over here, this becomes cosine squared of x minus 1 plus cosine squared of x. That's carefully distributing. And in the second term, well, what can I do here? I have a sine squared. And remember, I want it eventually all to be in terms of cosine. So I can do the same thing. I can put it in parentheses and now do the same thing. Replace sine squared with what? 1 minus cosine squared. All right, so now it's looking pretty good. Now not only are all the angles x, but all the trig functions are what? Cosines. So all we have to do is kind of expand it out, combine like terms, and see what happens. All right, simplify inside the parentheses first. Cosine squared plus cosine squared, that's 2 cosine squared, and then minus 1. And I still have that times cosine there. Details matter. That's the benefit of doing this stuff. You have to be logical, and you have to be meticulous. Minus. Now over here, this is where it can kind of get a little squirrely. You're going to distribute something from both sides. A negative 2 on the front and a cosine at the back. So really we're distributing a negative 2 cosine of x. You'll see that? A negative 2 cosine of x, then when you distribute it becomes negative 2 cosine of x. And then a negative times a negative is a positive 2 cosine cubed. We're distributing in from both sides. Yeah, you could call it, if you want to take another line and call it negative 2 cosine of x times 1 minus cosine squared, so that on the next line it's right there together, that's fine. Sure, absolutely. If that's what you need to do to avoid a careless mistake, take an extra step. All right, so now I took an extra step here. Now I have to expand this out, and I get 2 cosine cubed minus cosine of x, and then minus 2 cosine of x plus 2 cosine cubed. And now I'm at the point, I think, where I can combine like terms. I've got a 2 cosine cubed plus a 2 cosine cubed. That is a 4 cosine cubed of x. And then I have a minus 1 cosine minus 2 cosine is minus 3 cosine of x. And there it is. We have succeeded. We have written the entire expression in terms of cosine of single x. There's two terms. One of them's cubed, one of them's not, but it's all in terms of cosine of x. So what's kind of an interesting side note here is notice we started out with a cosine of 3 times x, and we ended up with a cubic function of cosine cubed. Just like on the identity itself, we start with a cosine of 2 times x, we ended up with a cosine squared. So in general, what's kind of neat to generalize is that if you have sine of n times x, or I'm sorry, cosine of n times x, you can write it as an nth degree polynomial in terms of cosine. So if you had like a cosine of 5x, you're going to be able to write it as a cosine to the fifth of 1x. That works for cosine only. It doesn't work for sine, unfortunately. Kind of an interesting little observation. Okay, I'm going to let you try it on your own. Prove the following identity. Give you a couple minutes to show that the left side equals the right side. And you've got all your fundamental identities that you can use. You've got the composite identities, you have the double angle identities, and you have all your algebra. All right, on which side did you decide to start on? The left. Good. Why, Callie? Thank you. She's not here. I haven't seen her in a couple of weeks. Yeah, on the left side, because you could split up the what? I'm sorry? The 3x. It has a larger angle, a denser nucleus, if you will, in the angle. And the ones on the right are all single angles. So step 1 is to write sine of 3x in terms of ultimately what? Single x, right? So we can use the composite identity first. Did you say 2x plus x or x plus 2x? 2x plus x. All right, cool. I'll do it that way then. It's the same, right? Doesn't matter. All over, did you do anything in the bottom? Sine x, cosine x? Yeah, you just kind of kept it. It's just kind of patiently waiting because it's already in terms of single x. Now you implement the sine composite identity in the numerator, which, remember, it's selfless. So it's sine of the first, cosine of the second. What happens with the sign? The plus sign? Stays or goes? Stays. Sine, same sign. And then sine of the second, cosine of the first. All over the product, sine times cosine. All right, so now we still have some work to do with the angles, which, remember, trumps everything. Very similar to on the previous problem, we need to write these in terms of single x. So now we don't have to use the composite identities again. We can just use the double angle. So sine of 2x is equal to what? 2 sine x cosine of x times the cosine of x that's there. And again, we don't need parentheses because that's a single term. Plus sine of x times, we do need parentheses here because the double angle for cosine generates 2 terms. What was it again? I tend to forget. Cosine squared minus sine squared. Excellent. That's the one that you can memorize. And then from there, if you need to, put it in terms of sine or cosine exclusively with the PIDs. All right, so the right side has 2 terms. Bless you. So let's go ahead and combine everything in the top and distribute. So in the first term, you can combine the 2 cosine factors, right? So you get 2 sine of x times cosine is cosine squared. Plus, yeah, we can't distribute. You want to? All right, we'll see what it does. It's not wrong. It can kind of, if it doesn't work, sometimes knowing what doesn't work can be kind of nice as well. You know, not to try it again. All over sine x cosine x. Okay, now in the top, does anything combine? Do we have like terms anywhere? We actually do. They have the same variable part, sine x cosine squared, sine x cosine squared. So 2 of them plus 1 of them makes 3 of them. So again, I'm not quite sure where this is going at this point, but I'm enjoying the adventure. It's fun. Like a Sunday afternoon class. Yeah, we could. Is that what we want to do? We have cosine and secant over here. You split them up? Yeah, at some point that's what you're going to want to do if you stay on the left side. And that would be kind of my next suggestion. You do have 2 terms over here. So the way that you can split up 1 term into 2 terms is by putting them each over the entire denominator. So if we do that, we have 3 sine x cosine squared all over sine x cosine x minus sine cubed x over sine x cosine x. So they have to each go over the entire denominator. And now you can divide out any common factor. Yeah. So in the first term, we have sine of x divided by sine of x. Those divide out. And then in the second factor, cosine squared over cosine, one of them divides out.
How does that not lose information?
It does lose information, but we are not solving a conditional equation. We are proving one expression is equivalent to another. So that's fine. It's not good when you're solving a conditional equation, because then you're looking for the conditions in which it's true. And when you lose variable information, you lose possible conditions or solutions. But in this case, We need to make that expression look like this. So we can get rid of information. That's a good question. Minus, one of the signs divides out, and we're left with sine squared of x over cosine.
We can turn that sine squared into 1 minus cosine squared. You get to that?
Very good. Yeah, if you come over here, cosine and secant are kind of both in terms of cosine, right? Because cosine is cosine and secant is cosine in disguise, 1 over cosine. So yeah, maybe you would do that. Seems fair. So 3 cosine of x minus parentheses 1 minus cosine squared of x all over cosine. And that's a little bit dangerous because you do have a negative out front. And let's go ahead and let's do two things in one. We'll distribute the negative and we'll split it up. So I'll be left with a negative 1 over cosine. And then a negative times negative, a positive cosine squared over cosine. So if you do that, I can follow that. Algebraically, that's fine. Distribute the negative, which is super important, and then put each term over the denominator. Okay, so now look in the third term, cosine squared over cosine. We're left with cosine. And now I have 3 cosine in the front, 1 cosine in the back for a total of what? 4 of them, right? Which is what I wanted. If you remember the right side, we needed 4 cosine. So we got 4 cosine of x. And now 1 over cosine, that's equal to what? Secant of x. Yeah, flip it. And you got the right side. Oh yeah, this is not that big compared to them. Orale. Yeah, that's in the grand scheme of things. That's not. You'll get used to them of that size if you do the worksheet expediently. If you try to do it the night before, you're going to be overwhelmed, and everything's going to be way long and way hard. We'll take our time on this one. Yeah, there's 2 more sets of identities to get through, but I would definitely start it. Okay. Is that the only way to do that problem? No. Are there probably shorter ways? Maybe. But does this method work? Yeah. Yeah. So if you get bored, you finish your worksheet early, go back through and try all the proofs again, but try them a different way. The more you know, the better you get. These are fun. Some people whisper the word when they're doing them. So much fun. Some people shout it. Okay. There's a few people that won't be here today, so I think we get to a good stopping point today. Okay? We got the double angle identities. Memorize them, memorize them, memorize them. And if you want to go to the worksheet and practice, that's great. On Monday, we're going to pick up with the power reducing identities, both of which, for the sine and cosine, also super important for the next level. More notes. So if you're not here,